it's not even putting anything in there. Don't take that for being empty. It's saying it is significant. Think of it as 0.00000 whatever. It's so low, it's not even giving you a value. This is quite an important statistic though. I'm going to imagine that it's 0.0001, just so that we've got something to look at. This is telling me that is my mathematical relationship, my mathematical linear relationship, is this going to be a more accurate predictor of y for a known value of x than just taking the average of the lot? If that is a significant result, then it's saying this is a better indicator mathematically than just taking the average bacterial density. Because that's what it's really doing. If somebody said, my supervisor said, what's the average bacterial density inside that Petri dish? I could add them all up, divide it by n, number of samples I have, to say, there you go, its average bacterial density is 3 million per centimetre squared, whatever units we're using. But he could say, at a temperature of 55 degrees, what amount of bacterial would I find? What bacterial density would I find? I could say, oh, it's 3 million per centimetre squared, the average. Or I could use this as a predictor. Is this mathematical prediction more accurate than my overall average? Because we've got two methods of telling our supervisors the answer. We could say, oh, it's the average. Or we could say, well, if you're saying it's 55 degrees C, well, actually, my mathematical predictor is better than the overall average. It's saying it's 3,100,000 bacteria per centimetre squared. It's a better predictor. And this ANOVA value tells us whether we should use the equation of a line to find the maths, or whether we shouldn't bother with that. We should just use the average, because that's a better predictor. If we've got a random pattern on our scatter plot, then the average would be a better predictor than the line that we try and draw through them. And it's the ANOVA sig value that tells us which one to use. As we do more examples, you will see this in action. But this is a significant result. It tells us that the equation of a line, in this case, is a better predictor than the average. Of course it's a better predictor than the average, because we've got a perfect relationship. Of course this one is a better predictor. When I scroll down, that's the number, or the lack of number that we use. Once we've found out that it's significant or not, we can then fill in the missing values from our y equals mx plus c, or if you like, y equals a plus bx. They're the same methods of describing the equation of a line. Different statistics textbooks will use different values of this. But we've got something called a constant and the intercept, and that's how I remember it, because that's old school kind of maths, and we know that they're the same. So how do we find those? Down below on the coefficients table, for a linear regression, we've got a constant of 32 and a centigrade value 1.8. They are the two missing numbers in my equation of a line. So if I choose one of these methods of expressing it, so choose value y equals a plus bx, which is really b times x, remember, in a mathematical equation. I don't have to write the multiplying it. In this case, if we wanted to find the relationship, a is the constant, 32, plus 1.800, that is b, times y, x. So if I have a known value of x, a known temperature, I can put it there, times it by 1.8, and add 32 to it, and I get the value of y. X is the value in centigrade, y is the value in degrees Fahrenheit, isn't it? What we've produced is some sort of conversion chart, if you like. This could be miles to kilometres.